Two stars, locked in each other's gravity, trace a perfect, endless dance. Give us their starting positions, and we can tell you exactly where they'll be 1,000 years from now. Now add just one more, a third body, and something breaks completely. The motion turns tangled, wild, unpredictable. No equation can capture it. No telescope can forecast it far ahead. One extra object, pulled by the same simple law of gravity, and predictability collapses into chaos. This is the three-body problem. So strange it became the heart of a famous novel and series, and so deep that wrestling with it cracked open one of the biggest ideas in science. That a universe can be perfectly lawful and still be impossible to predict. Start with what works. Two bodies, say a star and a planet, pulling on each other through gravity. Newton handed us the law. Every mass attracts every other, with a force that grows with their masses and fades with the square of the distance between them. For two bodies, that law has a clean, exact solution. They orbit their shared center in perfect ellipses, repeating forever. The very orbits Kepler had charted. Two-body gravity even conserves tidy quantities, energy, and momentum that let us pin the answer down on paper. With three bodies, there simply aren't enough of those anchors to go around. Give me their masses, positions, and speeds right now, and I can write a formula for where they'll be at any moment, past or future. This is the dream of classical physics. The present fixes the future exactly, the clockwork universe. For two bodies, the clockwork holds perfectly, and then we add a third. It seems like a tiny step, three masses instead of two, the same single law of gravity applied between each pair. But watch what changes. Body 1 is pulled by 2 and 3. Body 2 is pulled by 1 and 3. Each pull bends a path, which changes the next pull, which bends the path again. Everything is now tangled together. Three bodies, each steering the others in a constant feedback loop. The tidy ellipses are gone. The bodies loop, swing, and fling each other around, sometimes hurling one away entirely. It looks alive, it looks random, but there is nothing random here at all. It's the same exact law, just 3 times over. No new force, no special rule for 3, just Newton's one law between every pair. That's what makes the chaos so unsettling. It hides inside the simplest physics we know. And run it again, from almost the same start, and you'd get a completely different dance. No two are ever quite alike. Sometimes two of them pair off into a tight orbit and kick the third clean out of the system. Gravity, playing favorites. So surely we can solve it the way we solved two bodies. Just write the formula. For 300 years, the greatest mathematicians tried. Euler, Lagrange, the finest minds in physics. And they failed, not for lack of brilliance, but because, for the general three-body problem, no neat formula like the two-body ellipse exists. In the 1880s, a king offered a prize for solving it. Henri Poincaré took it on, and at first thought he'd succeeded. But correcting a subtle error in his own work, he found something far stranger than a solution. The paths could be so intricate that no neat equation could ever pin them down. He had stumbled onto chaos, decades before the word existed. The three-body problem was its very first home, and it gave birth to a whole new branch of mathematics. From that one failure grew a whole new branch of mathematics, dynamical systems, and even the seeds of topology. Not solving it turned out to matter more than solving it would have. And remember, this isn't 3,000 bodies. It's 3. The bare minimum that gravity needs to become unknowable. Which leaves only one way to know the future, not to solve it, but to simulate it, one step at a time. But simulation hides a trap, and it is the heart of this whole story. Take the three bodies and run them forward. Now make a second copy, identical, except you nudge one body by a hair, a millionth of a meter. At first, the two runs look the same. The bodies trace nearly the same paths. But the tiny difference grows and grows. The paths drift apart, then split, then diverge completely. Within a short time, the two universes that started almost identical look nothing like each other. This is sensitive dependence on initial conditions, first glimpsed right here in three bodies and gravity, decades before Lorentz gave it its famous name, the butterfly effect. A difference too small to ever measure becomes, given enough time, the difference between everything. Run a third copy, a hair different again, and it carves yet another path. As many futures as there are tiny errors, with no way to know which one is real. And now sit with the strangeness of that. The system is completely deterministic. The law is exact. There is no randomness, no dice. If you knew the starting conditions with infinite precision, the future would be fixed, down to the last detail. But you never can. Every measurement carries some error. And in a chaotic system, that error explodes. So the future is determined and yet unknowable, lawful but unpredictable. Those used to sound like opposites. Chaos is where they meet. Long ago, the mathematician Laplace imagined a mind that, knowing every particle's state, could see the entire future at a glance. Chaos quietly kills that demon. Not because the universe is lawless, but because it amplifies the tiniest unknown until prediction simply runs out. We tend to assume that if something is unpredictable, it must be random. Chaos teaches the harder truth. The rules can be perfectly fixed and the outcomes still beyond reach. We can still compute, of course. Break time into tiny steps, and at each one, nudge every body by the gravity it feels. Step by step, the trajectory unfolds. This is how we model planets, spacecraft, even whole galaxies. But chaos sets a limit. Every step carries a tiny rounding error, and in a chaotic system, those errors double again and again. So there is a prediction horizon, a window in which our forecast is trustworthy. Beyond it, simulation and reality drift apart, no matter how good the computer. Push the horizon further, and you must measure the start ever more precisely. The cost climbs without limit. Double the forecast, and you may need to square the precision. It's the same wall that stops us forecasting weather more than a week or two ahead. Weather is chaos, too. Even our own solar system has such a horizon. We can chart the planets for tens of millions of years, but not reliably for billions. There are even clever step-by-step methods that carefully conserve energy, so a simulated orbit doesn't slowly spiral in from numerical drift. But chaos itself, no method can cure. The takeaway is humbling. More computing power buys you a little more horizon, never infinite foresight. Now, a beautiful twist. Even though the general problem has no formula, a few special arrangements do repeat perfectly. Place three equal masses just right, and they will chase each other forever around a single figure eight, like a cosmic ballet. It's mesmerizing. And astonishingly, it was only discovered in the 1990s with the help of computers. There are others, bodies frozen at special balance points, where the competing pulls cancel just so. We call them Lagrange points, and every pair of bodies has 5 of them. They're genuinely useful. The James Webb Space Telescope sits parked at 1.5 million kilometers out, holding station with barely a nudge of fuel. 2 of those points are even stable enough to gather debris. In Jupiter's orbit, whole crowds of asteroids ride along at them, the Trojans. But most of these solutions are knife edges. Nudge them, and they tumble back into chaos. Only the triangular points we just saw are truly stable. Order in this world is the rare exception, not the rule. Astronomers also cheat, productively. Make one body so light it barely tugs back, and the math turns tractable. That restricted version is how most missions are actually planned. This is not an abstract puzzle. It shapes the real cosmos and what we can do within it. Our own solar system is a many-body problem. Over millions of years, the planet's orbits are, technically, chaotic. We cannot prove it will stay stable forever. Spacecraft turn the chaos into a tool. A gravitational slingshot steals a little speed from a planet's motion, flinging a probe across the solar system for free. The Voyager and Cassini trajectories were threaded through a 3 and more body dance, on purpose, by people who understood it deeply. Distant solar systems, stars with several companions, live and die by this physics. Some fling their own planets out into the dark to wander forever. Zoom out further, and star clusters and entire galaxies are just enormous versions of the same problem, millions of bodies, all pulling at once. It even inspired fiction. A planet orbiting 3 suns, its climate lurching between frozen and scorched as the chaos plays out. That premise is what carried the problem into pop culture. Mission designers now ride faint gravitational currents between the balance points, low-energy routes that thread the chaos to move spacecraft on almost no fuel. And the same mathematics of chaos governs weather, fluids, populations, even the rhythm of a heartbeat. The 3-body problem was the doorway to all of it. Step back and the lesson is profound. For centuries, science dreamed of a clockwork cosmos. Know the present and the entire future falls out. The 3-body problem broke that dream gently. The clockwork is real, the laws are exact. But knowing the laws is not the same as predicting the future. Determinism does not promise predictability. There are limits to foresight baked into the universe itself, not from our ignorance, but from the very structure of how things unfold. It's a humbling, almost liberating thought. Some of the future is hidden not because we're too dim to see it, but because the cosmos keeps it that way. And once you see it, you spot chaos everywhere, in a dripping tap, in markets, in cream swirling through coffee. The 3-body problem was just the first crack in the clockwork. So return to where we began. 2 bodies, a perfect, eternal ellipse. Add just one more, and you get a dance no equation can tame. 3 objects, one simple law, infinite, unrepeatable complexity. The universe, it turns out, can be perfectly lawful and still keep its future a secret. Deterministic and unpredictable both at once. That is the strange, beautiful gift of 3 bodies. A simple rule, 3 dancers, and a future that refuses to be written down in advance.